This video is going to show you some of the calculations with lenses, the formulas, not the actual examples. It's going to show you some math signs and a little bit more about the lenses. This is our spherical thin lens approximation, and I've got a converging lens on the screen right now. I'm going to draw a line through the middle. That's our line of refraction for our approximation. That's where all the ray tracing lines will bend. I've got an object to the left, so that's the light source. The distance between the light source, or the object in this case, and the center of the lens, we call that S. So it goes to the center of our thin lens approximation. And the distance to the image, we're going to call that S prime, with a little apostrophe symbol on it. And that goes from the image to the center of the lens as well. Our lens equation is 1 over the focus equals 1 over the object's distance plus 1 over the image's distance. Or the inverse of the focus equals the inverse of the object's distance plus the inverse of the image's distance. This converging lens is also called a positive lens. It's called a positive lens because when I use this lens equation, I'll put a positive f, or positive focus length, into the formula, as opposed to a diverging lens. A diverging lens says 1 over f is equal to 1 over s plus 1 over s prime. Same formula, but a diverging lens is called a negative lens. It's called a negative lens because I'm going to put a negative focus, or negative focal length, into my formula. Now the cool thing about these formulas is if they give you the units in inches, or they give it in yards, or meters, or centimeters, you don't need to convert anything. So when using these equations, you don't need to worry about converting everything over into standard SI, or metric number system, to do any calculations. Just keep all the units the same. Whatever units you put in, you get the same units out. Alright, so let's look at our generic lens here, and there's our lens equation. Light source is going to be on the left. Now, the distance between the object and the light source, I'm going to call that a positive s. That's always going to be our case. And I can also have a negative s, because it follows on the opposite side. I'll make it negative. So basically down the center of the lens, that's kind of our number line, and that's going to be 0. The image distance is a positive s prime if it appears where the light belongs. So light starts on the left-hand side, goes through the lens, therefore it belongs on the right-hand side. If the image appears where the light is, where it belongs, it's a positive s prime. If it appears where the light doesn't belong, so it doesn't belong back on the same side as the source, because the lens was supposed to create the image, then that's a negative s prime. If an image appears where the light belongs, that's always called a real image. So the light is actually going through the image. It would look as if it was standing there in front of you, or realistically right there, like what we think of as a hologram. Real images are always inverted, so that's a nice piece of information to find. So if I figure out it's a real image, knowing it's a positive s prime, I know that it's also inverted. Only converging or positive lenses can make a real image, so that can also help me tell me some things as well and help me out. A virtual image appears where the light doesn't belong, so it's when you get a negative s, that's a virtual image. And virtual images are always upright, or they're not inverted. You can think of it that way, as they never flip over. The formula for magnification is m is equal to h prime divided by h, which is equal to negative s prime divided by s. Magnification is a multiplier, so if you get a magnification of 2, it's twice as high. If you get a magnification of a half, it's half as high. Magnifications multiply. If you have multiple lenses and you find the magnification for each lens, to find the total magnification for the system, you just multiply all the magnifications together. If you get a negative magnification, that means you have a real image. Well, if you have a real image, that means it's an inverted image. So we know that a negative magnification tells us it's real and inverted. Virtual images, therefore, have a positive magnification, and they are not inverted. So negative m means it's not inverted and it's virtual. If the magnification is greater than 1, it's enlarged. If it's less than 1, it's reduced. It also helps that only converging lenses can enlarge. So when I'm talking about the magnification, I'm talking about the absolute value of that magnification. And we have our last formula. C is equal to r, which equals 2f. In other words, the center of our sphere is the same as the radius of the sphere, and that radius is equal to twice the focus. Or you can also restate it that the focus is half the radius, or half to the length of the center. And the last little tidbit of information: objects at the focus of an object of a converging lens, do not produce an image. So the rays never meet. So if you're putting the object at that focus, you're not going to see an image.